Okay, so now we want to look at free body diagrams that include friction. So we're going to be focusing solely on friction in this video. And just a quick review, remember that there's two types of friction, right? Static friction is the friction without motion, and kinetic friction is the friction that is associated with motion, and we give them two constants. This is the static coefficient constant, and then this is the kinetic coefficient constant. And then also, another review, this equation kind of relates the friction to the normal force, and we see that it depends on the coefficient of static or coefficient of friction, whether it be static or kinetic. It depends on which context you're given. And then also we should look at this diagram right here. Right here where something critical happens, this is where most of the static friction happens. And notice that as we apply more force, the static friction force increases along with it, right? Because you're pushing something, but it's not moving. Even though you're pushing harder and still not moving, that's because the static force is increasing as you go. And then once it reaches like a threshold value, which is called the maximum static friction, it kind of, I guess, flattens out here and it lowers actually. And this is the kinetic region. So this is the kinetic region, and then this is the static region. And then just a quick review, the reason why the kinetic is lower is because we need to look at the surfaces. So if we were to take a microscopic view, right, if we were to take a microscopic view, we would see that, let me just see, let's say the block kind of looks like this. If I were to draw it here, it's kind of rough, right, if we look at a microscopic view, and then the ground is also pretty rough, right? So it's harder to move the block initially because there's something called intermolecular bonds being formed here because they're not moving. And once you move it, once you're able to move it, those bonds break and it makes it so much easier to move. You can test this out yourself. Find something that you don't know that you can't move yet. If you push hard and you push harder, there's still static friction, but once you reach this threshold value, it's easier to push, like you don't have to apply as much force. And this is the reason why, because there's intermolecular bonds in the static, where there's the static friction, and then once you move it, it's easier to move because the bonds are broken. So we're going to be looking at two examples of free body diagrams with friction. So here's the first case, kinetic friction on a level surface. And I described this with this picture here where the squiggly lines indicate that there's a rough surface along this path, right? So I'm just gonna do that, and we are pushing the box with a force of this much, right? We're going to call this our applied force, so I'm going to give it this name, F sub A. So now we want to look at the free body diagram of this body. So if I were to draw it as a dot, we have of course, the weight of the object, the normal force of the object, which is capital N, and then we have our applied force, and then since there's friction, it has to oppose the motion, so we have a friction force here. And since it's motion, I'm going to give it a kinetic subscript, okay. So here it is. Now we want to look at the Newton's second law, and since from our previous thing we know that friction is related to the normal force, let's actually do the normal force first. So let's look at the y component. There's no motion in the y component, so it's set to 0. So, and if I define this way and this way as the positive directions, then we can just go normal force minus mg, which is equal to 0. In other words, normal force equals mg, and we've done this example many times before. It's just now we have friction going in the horizontal direction. So now let's actually look at the horizontal direction. The force on the horizontal direction is some acceleration force, right? So we have the applied force minus the kinetic friction force is equal to ma, and recall that the friction force is equal to the coefficient of friction, whatever it would be, and the normal force. So in other words, since it's kinetic, we want the kinetic coefficient, so it's mu sub k. We found the normal force right here, so it's mu sub k mg. Mu sub k mg is what it is. So let's actually just keep going. We have F sub A minus mu sub k mg, which is equal to ma, and then I guess maybe they give you all the values and they want you to find the coefficient of kinetic friction, so we just solve for that. Mu sub k equals, let's see, I'm going to bring this to the other side and then divide by negative mg. Let's see, so it'd be ma minus the applied force, all divided by negative mg. And this is just getting through the process. You don't have to like remember this equation at all, even though it's a weird one, so it's not really helpful to memorize these random equations, but rather just go through the motion or go through the process of solving for it, which is much more better than just memorizing the end results for specific cases. So we're going to look at one more. So here's the second example, static friction on an incline, and this is probably one of the most interesting examples, and it's probably one of my most favorite examples because it's kind of interesting what the result would be, and maybe you want to try this out yourself, but the result's actually pretty interesting. What we want to do is actually find an equation to find this, the static coefficient of static friction, right? So let's actually start. Let's look at the forces on this object. So we have the weight, we have the normal force, we have a friction force, a static friction force. So let me just label all these now. We don't have a force pointing this way because we see that it's not in motion, and this the parallel component of gravity actually will be the one that's counteracting this static friction. So let's actually look at the diagram. The free body diagram would look like this, right? But I actually want to tilt it, right, with an incline. We saw that in the normal example. So again, we want to look at the change, right? We want to kind of tilt it so it looks something like, oops, not like that, right? So if I were to convert this diagram to here, it would look something like this, because notice how these are actually perpendicular to each other, and this is kind of the real reason why we tilt the axis, because we have more forces that are I guess perpendicular to axes than a diagonal one. And of course this is the angle that I'm talking about. I described how this angle is related exactly to this angle in the normal force video. So there we go, let's continue. Let's actually break it down into its components. So again, we have to draw another diagram. So we have this much, this force, we have this force. Let me actually draw it solid. We have this force, this, and this, right? This is the static friction, this is the normal force. And now let's look at this. Since this side right here is adjacent, this is the mg cosine. And since the other one's the opposite of the angle, right? The one that goes like this one's the opposite one, this one's the sine. So this is mg sine. So now let's continue using this. Now we want to look at the Newton's second law, not the free body diagram. We just did it right now. So let's look at the normal force. Since we know normal force is related to friction, we want to probably solve for the normal force first. So net force in the not the x direction, we are defining it to be the perpendicular direction, right? And then let's actually, I'm just going to use this convention, right? Like that. The perpendicular one, which is equal to, it's not moving at all, so it's just simply normal minus mg cosine theta, which is equal to 0. In other words, the key equation here is normal force is equal to mg cosine. And then now we want to look at the parallel. So the net force of the parallel is also not moving, right? Static friction means no motion. It's not related to any type of motion, while kinetic is related to any motion, even constant velocity. So you might even have some cases where you have motion, but the net force is 0 because of constant velocity, and it's still kinetic friction. But in this case, the object is not moving because it is static friction. So now we want to look at this. So I defined it Fs to be in the positive, so this is the positive one, minus mg sine theta equals 0. In other words, let me just scroll down here. We have kind of officially went away from this diagram, and now we're on the equations focused on solely. We want to substitute this, right? Substitute this with the u sub s normal force minus mg. Let me actually bring that to the other side of the equation, and then we'll see something interesting here. We know what the normal force is equal to. Let's actually substitute that in. And then we get something pretty interesting here. If I were to solve for the coefficient of static friction, I get mg sine divided by mg cosine. And this is the interesting result that I found really interesting the first time I did it. It is actually just equal to the tangent of the angle. So it doesn't matter about the mass of the object at all. For this case, the static friction actually only depends on the angle of the incline, which was kind of interesting when I first saw it. We don't even care about how heavy the object is or anything else. We don't even care about gravity because they cancel out too. So the only thing that matters is the angle of this incline. So if I were to say like the object starts slipping at 45 degrees, we can find the coefficient of static friction just by plugging in tangent of 45. So again, just a quick review. These problems, they're not really like, you shouldn't like memorize the end result. You should rather memorize or know how to do the process to get to the end result than the memorizing the end result, right? This one's kind of a cool example. This one's actually my favorite example out of anything in dynamics, is this example specifically, because we see that mass is just not even important in this problem. And then again, remember that the static friction increases as you apply more force because it's not moving, so it has to counteract your force. And then once you reach this maximum value, it starts to flatten out this way and actually becomes less because intermolecular forces become broken. So that's it for friction. We're going to be looking at something else in the next video where we not only look at one body, but two bodies at the same time. So two or more bodies. So that's it for this video.